Good morning, everybody. We'll just wait a minute or two before people can join in. But for about a minute before we start. Okay, folks. Hello, everyone. Good morning. On behalf of my colleagues, welcome to this month's talk from Johns Hopkins Institute for Autonomy seminar. This is a series, as you know, we have been holding it every month. It's co-sponsored by the Computer Science Department of Whiting School of Engineering. Each month we'll have a talk on research topics that's at the intersection of assurance and autonomy. For information, this seminar will be recorded. Today's speaker is Dr. Larry Peterson. Larry Peterson is the Robert E. Kahn Professor of Computer Science Emeritus at Princeton University, where he served as the chair from 2003 to 2009. He's also a co-author of the best-selling networking textbook, Computer Networks, a systems approach. If you haven't read it, please read it. It's a very interesting book. And also now available as open source on GitHub. Dr. Peterson's research focuses on the design, implementation, and operation of internet-scale distributed systems, including the widely used Planet Lab and Measurement Lab platforms. Some of you might have used that. I used it when I was at Belcore. He's currently working on a new accesses cloud. It's called CORD, C-O-R-D. That stands for Central Office Re-Architected as Data Center, which is an open source project at the Open Networking Foundation, ONF, where Larry serves as the CTO. Professor Peterson is a former editor-in-chief of the SCM Transactions and Computer Systems. And he also served as program chair for many conferences, Hotnets, NSDI, SOSP, just for example. He's a member of National Academy of Engineering, a fellow of the ACM and IEEE. He's a recipient of 2010 IEEE Kobayashi Computer and Communication Award, and 2013 recipient of ACM SIGCOMM Award. Dr. Peterson received his PhD from Purdue University in 1985. So today, Dr. Peterson will talk about the network as a programmable platform. And please put your questions in the chat box, and these will be answered after the talk. With that, let's welcome Dr. Larry Peterson. Larry, is over to you now. Larry's over to you. You're on mute.
There, can you hear me now, finally?
Yes, Larry. Go ahead,
all right,
please.
sorry about that. I was having trouble hitting the mute, getting to the mute button. Well, sorry about that little snafu at the beginning, but let's get going. Yeah, so my talk today, I've entitled it "Network as a Programmable Platform." Computer science is out building platforms all the time, but it's kind of interesting if you think about the history of networking. We've never really talked about networks as platforms. We more think of them as plumbing. And you know, we wire up networks, and we use that as a building block to build larger, interesting distributed systems. But what's been happening over the last few years is that the network is in the process still of being re-engineered in a way that makes it also a platform that can be programmed. And so I'm going to be talking about what that means and some of the implications as well. And just let me note that this is work that's in collaboration with a lot of people, including the ones that you see listed here. And it also has a pretty large collection of open source behind it that's coming out of the Open Networking Foundation. Okay. So what I'm going to do in this talk is start out by talking about what SDN is meaning to networking and where the software-defined networking initiative is taking us and how it's changing networking. Again, where it's taking us is that the network is going to be, we can treat it as a platform. Then I'll talk a little bit about what that means for networking in general. And that's networking in general that work is coming primarily out of the hyperscalers. Google and Azure and so on are being built using much of the ideas I'm going to be talking about. But those ideas are now being applied to the cellular network as well. And so I'll spend a fair amount of time talking about how that's happening. And as I mentioned, there's a lot of open source software, which means that there's now an opportunity for everybody, particularly in the research community, to get involved. And so I'll introduce Aether, which is an open 5G enabled edge cloud. And I'll talk about what that means and the kinds of research opportunities it opens up. So let's start by talking about that SDN journey. And it's been, like I said, it's been going on for a little while now. And the idea behind it was actually can be explained very simply by looking at what happened in the computing industry. We started out with very large, monolithic, bundled computing mainframes. And they were closed and proprietary. They became increasingly complex, and there was little incentives to improve them because you got locked into a particular solution. The same thing could be said of network mainframes. The large core routers of the internet were very much the same way. In fact, it's kind of hard to tell them apart just looking at the pictures. Well, these turned out to be very hard to manage. They were very hard to secure, and they were, most importantly, I think, very hard to change. And so what SDN has been about is sometimes summarized as just calling it disaggregation, that we've basically broken those big bundled systems down into some elemental and commodity components. And so in the networking case, well, you know, the computing case, that's the PC and the whole ecosystem of software that runs on, on that hardware. In the networking domain, there's a counterpart, which is its white box switches, and that implements the data plane built out of merchant silicon switching chips. There's a lot of open source software you can now run on those boxes, and the control plane has been lifted up to run in servers in the cloud. And so that's also brought the best practices of building scalable cloud services to the network. And as a consequence, the argument is pretty strong, and the experience has been very strong like I said, at the hyperscalers, that the network is now easier to fix, it's easier to innovate and add new features, and it proves to be simpler to operate as well. Now, this is, maybe you've already heard the SDN story, and so this is just a summary of it. But as a consequence of this being set in motion, it's also now the case that you not only have lifted the control plane, but it's now currently happening that you go down into the forwarding plane, into those switches, into those switching chips. And there's a lot of activity down there as well. So what I'm showing here is a fixed function switch that you might typically buy. And by fixed function, I mean it had built into the ASIC the exact set of tables it was going to do lookups on as your packet flowed through. And these are typically structured as pipelines so that I can be doing multiple lookups in parallel as a stream of packets processed through. Well, what is now happening is that the forwarding plane is also programmable. And it's basically the very same abstractions that SDN brought to bear on the control plane, which is that you instruct the data plane to take a particular action whenever it matches a particular string. The same thing now gives us the ability to program those pipelines. So instead of a set of fixed tables, what we have instead is a set of programmable tables. There is a programming language. There's lots of opportunities there as well, but the programming language that's typically used to program that pipeline is called P4. It looks a lot like C, except it's taken out loops and it's used in a more declarative way. And there's a tool chain behind that, but as a consequence, we're able to change the behavior of the forwarding plane in the pipeline as well. And so, like I said, this is still happening, and there's still certainly a lot of fixed function switches out there. But because of the programmability that's happening in the programmable pipeline space, in additional programmability is also creeping into the fixed function switches. So eventually, this will converge and give people that own and operate networks a lot of control over the actual behavior of their forwarding planes implemented in switches. So that's a little bit of a summary of the SDN journey and where it currently is. What does all of this mean for networks? Well, what it means is that the network is now programmable both end to end, from the source to the destination, and from top to bottom, from the high level specifications all the way down into the silicon that forwards packets. And so the switches are P4 programmable. There's a lot of work going on to build the network interface cards to also be P4 programmable. And the virtual switches, which you probably are aware because of the number of virtual machines that are running relative to the number of physical machines, also are now P4 programmable. There are other ways to program them, but they are also P4 programmable. On top of that, then there are now multiple SDN controllers, including open source controllers. And you can think of them as the operating system of that distributed forwarding plane. And they host a set of applications. So you can run a routing application, traffic engineering applications, load balancing, and so on. The key idea here is now the switches simply do what they're told. And in fact, I can program them because I can program the forwarding plane. And I collect information from all those switches. I make globally optimal decisions. And then I push down the behavior, the forwarding rules that I want those switches to implement. Well, as a consequence of that now, it is possible to specify at a very high level the behavior that I want from my network. It's then compiled. Pieces of what get compiled are partitioned and distributed end to end across all those programmable components down there, recompiled at every level. This is all possible because there are now some well-defined interfaces at every level. And as a consequence, now I have the ability to program again at a very high level. So this makes verifiable closed loop control a real possibility. And so what I mean by that is one of the ways that I can program that network is to collect very fine-grained network telemetry data. And I can literally program the switches to watch for particular patterns of packets, particular behaviors, and output information as monitoring information as a consequence. It's not a fixed function anymore. And so I get from the network now a sequence of messages tell me about what that network is doing. And I have the opportunity to feed that observational data into a verifier and check it against the high-level specification. And I can now, by observation of what's going on in the network, verify that the network actually implemented the high-level specification that I wanted it to. Not only that, but because I now have this information about the network's behavior, I also have the opportunity to close the loop. And so I just showed you that maybe you do verify, but maybe you don't verify. I have the opportunity to now go back to the top of that stack and change the behavior, change some parameter, change one of those algorithms so that I get the behavior that I want. So I have verifiable closed loop control. So where does this leave us? Networks are now starting to be, for the first time, programmable end to end. We have the opportunity to specify them top to bottom. Would not yet claim that that is standard practice, but we do have that opportunity. And they are entirely defined by software. It is a programmable platform. The kinds that we're used to taking control of and specifying their behavior in the computing side, we now have the same opportunity on the networking side. So this means that networks are now correct by construction. I am able to construct their behavior top to bottom. I can then verify against that specification in case there were adversaries attacking it, and I can correct it and adjust it through closed loop control. So this is the promise of having the network as a programmable platform. Now, this is where we'll transition now. This is what's going on. And like I said, there's a lot of activity in the wired network, but if we're really truly going to make this end to end, it sort of begs the question, what about the cellular network? And so what I'm going to spend a little bit of time now is peeling back what's going on in the cellular network and talking about how these same ideas also apply there. By the way, once I get there, I've got a whole new set of applications, right? Because I'm now in the mobile world, and so handover control might be my counterpart to routing. I still have the opportunity to do link aggregation, load balancing. A lot of the same problems are still there. One of the questions is it also P4 programmable? Because that was part of the equation I showed you earlier, and the answer is it still needs to be done, but there are opportunities to do that. So let's again just talk at a very high level about what 5G is meaning to the redesign of the cellular network. And so this is a very simplified high-level description of the 4G network. And the thing that you observe from it is it looks a lot like the wireline networking industry did several years ago when we started out with those monolithic bundled routers. We have bundled proprietary eNode Bs. Those are the base stations. There's a software stack running in there, but it's bundled together and hard to break apart. And the evolved core is effectively the router that connects the RAN to the internet. And historically, that was closed and also a telephony-based system. It has also started to open up and become disaggregated. So there's actually now quite a bit of open source software there, but at one time it was an equally closed system. Now, I won't go through the details of it, but if you conceptually break open the base station, it is a switch. It happens to have a radio attached to it, but it is a switch, and it has a software stack that would be very familiar to someone that understood what a software stack looked like in a router, because it does make forwarding decisions to forward from one eNode B to another to ultimately to reach the end user device. Now, what's happening with 5G is, again, disaggregation. So we're taking a piece of that stack and we're going to still bundle it very close proximity to the radio. I'm showing a tower here, but don't necessarily think tower. We have small cells now, so these are going to look just like the access, potentially look just like the access points that you have for Wi-Fi. There's a subset of the stack that's going to be running in a distributed unit, and there's a subset of the stack that is going to be more centralized. The relevance of the sort of the color coding here is that the gray tends to be down at the digital signal processing level, very close to the radio. These are some data plane transformations that get done to the data. For example, you take a large IP packet, you have to fragment it into smaller chunks to transmit it. Scheduling decisions about which fragments to transmit get made in here. The central unit is where color code red means that there's some control decisions being made. And so that's going to become important as we sort of adjust this to the SDN model. The core, I'm not showing you what the 4G core looked like, but the 5G core looks an awful lot like a microservice-based architecture. The specification doesn't require that it be microservice-based, but it has notions of message buses and notions of different sorts of stores and stateless behavior. So a lot of the best practices of building microservices can now be applied. So the big takeaway here is that we have a lot of open source available across the stack, and it's a microservice-based design. So if there's sort of one takeaway that from my talk, this is what I would have it be. When we started this process, the access network sort of lived at the edge of the cloud, and the cloud connected to the access network, but it did not subsume it. What is actually happening now is that line is moving all the way over to the left-hand side. And so all of these pieces that had been part of the closed proprietary bundled 5G or 4G, now 5G core is and RAN is now effectively part of the cloud. And that has huge implications on how that will evolve over time, because we're now in a regime where feature velocity becomes the dominant concern. And we have the opportunity now to roll out new versions of all of this software, to customize the software to meet different needs and so on. The other thing that it gives us the ability to do is to take everything I was talking about earlier on the SDN side of things and apply it to that, to the radio network. And so we're going to take that control piece out, and we're just going to turn that into an SDN controller. It's exactly the picture we had before. In this space, it gets called a RIC, but it's an SDN controller. RIC stands for RAN Intelligent Controller. And it's going to control the various units that are then distributed throughout the RAN. And it runs a set of applications. So I have disaggregated the RAN and restructured it as an SDN application. On top of that, there's still a management plane. Don't forget, this did come out of the telco world. So if you're familiar with that terminology, there's an OSS, BSS. There's a lot of machinery up there because operators obviously spend a lot of time operating their networks. It's also where policy can be defined. As an aside, this has been democratized at the same time, so you don't have to have the wherewithal of a global carrier to deploy this. There are management planes that are extremely lightweight that are being built, and they're being built according to the same ideas that are happening down here in the core, in the microservice-based design. But where I wanted to get to next is we now have multiple control loops that are available to us to program and take ownership of. And so there's a non-real-time control loop that runs up at you set the policy up in the management plane. The RIC is considered a near real-time control loop, so you can control and make decisions to change the behavior network in a loop that is on the order of 10 milliseconds. And I didn't talk about it in any detail before, but there is still the very fine-grained real-time control loop, and that's the scheduler that runs down in the distributed unit. So that's literally making decisions every microsecond or so as to which packets to transmit next. But that's also now available in open source that you can go in and modify it, and you can certainly control it from above. So I mentioned that P4 is taking over the programmable pipelines. What about P4 in the data plane and the forwarding plane of 5G? Well, there's two relevant components, which is the data plane piece. It's called user plane in 5G speak. The user plane component of the core, and in the central unit, the topmost data plane / user plane component of the central unit. This is problematic in some ways because there's some state that needs to be maintained, but it's certainly in the case of the core, the next generation core, the component there that's called the UPF, the user plane function, is now being re-implemented in P4. And so this is going to get a little detailed for a second, but just for the sort of the high level idea, I'm going to just walk through what that means. It's also a little confusing because we now have different domains that are being controlled by SDN controllers. So the RAN is being controlled by one controller called the RIC, and the core, in particular, the UPF, is being controlled by another plane. And the reason we're going to do that is this controller is also going to be controlling the regular old commodity switches that I have put functionality into using P4 to implement the user plane function. So let me show you what that looks like. So if I just blow up the UPF, again, this is the core component of the cellular network. I can bring my programmable switches into it. And so I have a data pipeline between the radio unit and the internet that passes through a programmable switch. That switch is going to be connected to a server or some number of servers. And those servers are going to have NICs and dumb NICs and smart NICs. I'm just showing you all the possibilities. The control plane that I mentioned before is still running up above. This is just a detail. There's a particular, to be standards compliant, there's a particular interface you have to speak. But the important point that I want to make here is that the switch is programmable, the smart NIC is programmable. I didn't label it dumb NIC, but a traditional NIC is not programmable, but the virtual switch that runs on top of it is programmable. And so now everything I told you before about, programmable top to bottom applies. And in fact, there are two different forwarding paths that are available to you. One of them I'm just going to call the software path, which has to go up into the server where it encounters the virtual switch. The other is the hardware path. And the point is, you would like the hardware path just to go through the programmable switch, but there's not enough capacity in here for everything we want to do right now, eventually perhaps. And so you might visit a smart switch as well. So a little bit of detail, I'll just run through this really quickly. There's tunneling that goes on that's easily implemented in today's programmable switches. There is QoS and other buffering that takes place up in the smart NIC or in the virtual switch on the other side. But progress is actually being made, and these are moving down into the switch. So it will be the case in the not too distant future that you can connect to the entire mobile core and implement it entirely in the very same switches that you're implementing the rest of the IP network, the TCP IP network. So the deep programmability is there even in the cellular case. So I mentioned, so that's sort of let me go back to, oops, I shouldn't have done that. Going back to this picture, so we did a little bit of a drill down here. I'm going to go do a little bit of a drill down here and look at the SDN controller that controls the RAN. Apologize for my having to go through the animations again. Okay, so we have an implementation of that. You might be skeptical that you could actually control a RAN through a centralized RAN intelligent controller, but it is in fact the case. The RAN that the RIC that we are building is built out of ONOS, which is stands for Open Network Operating System, which is the very same SDN controller that we have been using to control the more traditional Ethernet switches that we build data centers out of. If you broke open ONOS, you would find a number of subservices because it is itself built around a set of disaggregated functions. And all that really got added from the more traditional ONOS to make it a RIC, well, is it still has to speak all of the standard 3GPP interfaces to everybody else, both northbound and southbound. These interfaces, by the way, are being defined by a consortium that it is attempting to open up the RAN, so they're clearly motivated to define those interfaces. The only thing that was added here is really the collection of the telemetry data that allows you to then make the load balancing and the handover and the link aggregation decisions that you need to make. And performance is quite acceptable. For example, handover performance, as you scale up the number of devices, those are what the UEs or user equipment, those are the devices. As you scale them up, you can see the effects 95% of the time. For example, you're getting your handover done in just a couple of milliseconds. So it's and you can scale this thing up, right? Because this is now a cloud service, so you can scale up the RIC. So this is just a little proof point. There's a lot of ongoing work here, but the ONOS-based RIC is both a feasible and workable way of controlling a RAN. It also, most importantly, is open source. So now I have, not only is all of this programmable, but it's programmable using open source. So where does that take me? It takes me to pulling all of these parts together to build an edge cloud. And at ONF, we call that Aether. It's a managed 4G, 5G edge cloud, and it's intended for deployment in enterprises. Those could be university campuses, they could be manufacturing plants, they could be business enterprises as well. So we're going to take advantage of small cells. We're going to be able to build this ourselves as opposed to just viewing this as something that's offered by a telco. This is private 4G, 5G way of approaching the problem. So here is the high-level picture of what Aether is. Think of this as its value proposition. I go into a premises or an enterprise. I deploy a small cluster. It's an edge cloud. It literally is going to be running Kubernetes. I connect a set of small cells to it. In the US, those small cells could be CBRS, use a CBRS spectrum. Other countries, there is other unlicensed or lightly licensed spectrum available as well. And my enterprise is now, reinventing itself as a set of IoT devices and sensors and cameras and so on. So the whole, reinvention industry transformation 4.0 is sometimes a marketing term that's given to that. Enterprises are reinventing themselves in the cyber physical world. We can control those devices using small cells connected to an edge cloud running open source software. And so on-prem is the SD-RAN component, the software-defined RAN that I showed you a minute ago. There is also the software-defined core, the user plane component of it. And now I have the ability to run edge apps here that needed to be in close proximity to those devices for latency reasons primarily. This is called local breakout. It's one of the important ideas that I do not have to go all the way back up into the perhaps distant central telco to turn my data around. I'm able to basically have work hit an application, traffic hit an application without ever leaving the premises. That not only has performance implications, but it has really important security implications as well. My data does not go off-prem. There is still a central component. It runs in a central cloud. I'm just generically saying central cloud here, but when we run Aether, we run that in Google's cloud. We've run it in Azure and Amazon too, it doesn't really matter. This is where the control plane component of the core runs. There typically also are counterpart central applications associated with the edge apps. So I might be doing inference, machine learning inferencing at the edge, and I might be doing the learning back in the cloud. And so on. Pretty much all of these apps have both an edge and a central component. And there's a management plane because I offer this as a managed service. And so the enterprise operators or system admins log into this control plane to control what happens. So that's the high level picture. I wanted to spend a few minutes walking through the details, and you may or may not care about the details, but the big takeaway here is I'm going to show you a whole bunch of open source commodity components that I can assemble to create that picture that I just had up a second ago. So we start with commodity servers and white box switches. And they boot with nothing on them except a bootloader. I'm showing this, might look a little upside down to you. The reason I've got the servers on top of the switches is just because that's where the software is going to run and the software controls everything. The topology of the switches is a leaf spine fabric. So these are the spines and these are the leaves. I'm showing a single leaf per cluster. This is just a cartoon of what a real cluster looks like, obviously. But this is the same structure that the hyperscalers are building their clouds with, except on a smaller scale. It could be a partial rack. It could be, half a dozen racks, full racks built out. So you can build pretty substantial sized clusters at the edge using this technology. We're going to run the standard SDN stack, which includes a network operating system, and it includes a switch operating system. So the network operating system, I've already shown you what we run. It's called ONOS. The switch operating system just gives me the ability to treat that switch like I would in the other server. It's got a northbound API, and I can configure it and control it from the centralized network operating system. SD Fabric is just the name. I'm sort of characterizing the main app that runs inside of that network operating system. It's the app that understands it's controlling the switching fabric. These switches are P4 programmable. I'm not showing that explicitly here, but I have also loaded the program into each one of these switches that decides how it forwards packets. And so there's a P4 implementation, also open source, that does that. This whole thing is managed as a Kubernetes cluster. So I'm not showing you the internals, but this is a bunch of microservices running in Docker containers. And perhaps a little bit unusual, we also view the switches as just another processor I load a bunch of microservices onto. So that it is also controlled by Kubernetes. So now I have a commodity hardware stack that I load microservices onto using Kubernetes. So let me remove Kubernetes because it gets in my way. and show you that the next thing I do is I simply attach one or more small cells to one of the leaf switches or multiple leaf switches. So I built out a RAN in my enterprise. The next thing I run on my switching on my cluster is the SDN RAN. That's that whole RIC and all the applications that go along with it. Again, a set of microservices. I'm not showing the details. It's controlling the small cells. The third thing I run is the user plane, the UPF of the SD core. So now those are all my workloads. And so if you think about what you have here, it would be what would look like a traditional, conventional Kubernetes cluster, except I also have the ability to communicate with the devices that talk over this via the small cells. So let's package that whole thing up, and in Aether we call that ACE. It's the Aether Connected Edge. By the way, I'm not showing other edge applications here, but I have sufficient capacity to load up. Just as an example, Amazon's Greengrass. It's their IoT platform. I can load that on here. You may have other apps you want to load there. I have the ability to scale those across a set of sites. So these could either be all of the sites that are part of my enterprise, or it could be you could view this as a managed service that different enterprises subscribe to. So this whole thing can be multi-tenant if you want it to be. In fact, that's the way we run it. There is a centralized piece, as you saw before, and that's where I'm going to run the control plane of the SD core. And it's also where I'm going to run the Aether management platform, AMP. Now, I'm not going to do it here, but in my view, what goes on inside of this management plane is hugely important, because it's the place that gives me the ability to gain the feature velocity advantage of the cloud. And so every time a developer creates a new bit of functionality to improve one of these components, it gets checked into GitHub. And there's a pipeline that runs here that tests it and integrates it and puts containers out into repositories and all of the configuration information, so that I can then not only continuously develop, I can continuously integrate, and I can continuously deploy those fixes. And so we have a very short turnaround time to deploying integrated, tested software into the connected edge. You then collect a lot of monitoring data about how that thing is behaving. You then feed that back into the dynamic, the closed loop control that I've been talking about. So this is an extremely important and powerful part of this, and necessary part of the system that's often overlooked because it's just management. But I think it's really one of the keys. And again, this is all open source as well. So this is the sort of from the ground up description of what happens in Aether, or the implementation of Aether. Aether is actually an operational deployed system, managed service. So ONF is a little tiny operator. For many years, just a couple of words about ONF. ONF has as its partners a set of network operators. Over time, it's included AT&T, Comcast, Deutsche Telekom, NTT, and so on, and a set of vendors that are providing them with solutions. But typically, those vendors have been ones that are interested in disaggregated solutions, as opposed to the more traditional vendors. So Intel, just as an example, for obvious reasons, is one of our partners. But in any case, ONF for many years was producing open source software that the telcos would then subsume, and they would go do their thing. What we are doing now is actually operating this, and we have it's a small deployment, but we have the central piece runs in the Google Cloud, and we have ACE pods deployed at a number of places around the globe. And we're concerned about uptime and have an air budget and everything about managing cloud services. Those principles apply to our operations team. And trust me, you learn a lot about a system when you have to operate it yourself. And just one other highlight here is that very importantly, we're going to do a field trial with DT the last half of the year. It'll be an outdoor deployment of Aether. And there's a whole bunch of partners that are involved there, all bringing pieces, and it's going to be an open source, RAN, integrated deployment. So Aether is something that is, it's open source. You can get the code and you can look at it, but it's also something that you could bring up an ACE pod on your local campus. So let me shift just a little bit. I've been talking about this whole stack of what's possible. And in some sense, it's all getting you to this next little bit that is going to be my conclusion, which is Pronto, just to throw another project name at you. Pronto is a DARPA-funded research project. It runs on Aether. So if you think back to my title slide, and I talked about our collaborators at Cornell, Stanford, and Princeton, those are all part of the Pronto project using Aether as a deeply programmable platform on top of which they can build secure networks. And so I'm not going to spend a whole lot of time here, but just to kind of give you a flavor of what's possible. I'm just showing the same picture I had on before, except I just want to highlight that there is now a place that the researchers are able to plug in their new ideas and test them. And so in-band network telemetry, we are collecting very fine-grained data, and we are changing and controlling the switching fabric so that we can change in real time what data gets collected. So if, for example, you believe there was a problem, you could load the appropriate tables in the switches because you programmed those switches to catch fine-grained data about a particular flow, and then maybe observe what was going wrong. We are feeding that into some verification tools, and just the visibility and control and the ability to come back in and change this is sort of the proof in the pudding of the system. And so the demonstration application that we're using here is flying autonomous drones. And so we're flying a set of drones in formation. At Stanford, there is a lab that they have set up where they've been working with autonomous drones for some time. We've now connected them to the network that we're building here, the Aether network. These drones are controlled via the small cells from a drone control program that's now an example of an edge app that runs in the edge cloud. There are different ways of then driving and giving your intent to this control program. That the flyers can be remote, but another option is that the flyer is automated in a closed loop. And so there is a motion capture application, edge app, that also runs, and the room is instrumented with video cameras. And so what basically is happening is that I am observing and collecting video connected into the switching fabric. I'm sort of trying to animate the path here to the motion capture app. The motion capture app does image processing, sends instructions to the drone control program, who then also over the fabric and through the small cells tells the drones how to fly. Now, at this point, there are a set of demos. I had a little trouble getting them going, and they aren't, visually all that impressive right now. It'd be really impressive if you were to attack one of these switches and the drones caught fire or something. That doesn't quite happen. They just safely land because you don't want to crash drones in a lab. They're expensive to replace. But we have, if you go back to verification, closed loop verification, we have launched a variety of attacks against these switches, and then the countermeasures can also be deployed using the end-to-end programmability that I've been talking about. So, in summary, deep programmability is the linchpin. There's a sort of a call to action that my co-authors and I published last fall in CCR. There are several project websites you can visit. The demos are not there today, but hopefully within a week they will be there, probably both on the Pronto website and the Aether website. Just call attention to SD-RAN. It is a sub-project of this whole Aether endeavor. This is work being done in collaboration with the ONF partners. In particular, AT&T and Facebook are big partners in this. But if you're familiar with the activity going on there, in addition to the 3GPP standardization that happens, there's now an Open RAN Alliance that is trying to drive all of this so that it is as open as can possibly be. And the near real-time RIC that I talked about earlier is an output of that, and it's all listed under the SD-RAN website. Finally, my experience has been that a lot of the people that we're trying to bring into this space that maybe come from the more traditional cloud space and didn't know a lot about 5G, we found that actually starting with the tutorial to explain what 5G is about and what its internal pieces are is an important starting point. So if you don't know 5G in any detail, or you don't know SDN for that matter, there's a couple of other references that you can go to. So I think with that, I will stop.
Yeah.
And we can go to some questions.
Thank you, Larry. Excellent presentation. We have a few questions. I'll open it up to the audience first, then I'll go back to the panelists. Got about maybe 12 minutes or so. So the first question from Harold Jang, for the current industrial implementation of SDN solutions, vendors such as Arista, Aruba, Cisco, Juniper still prefer to associate control functions closely attached to the data plane, especially in their switch products. They claim the classical SDN protocol, such as OpenFlow, is not scalable. Do you have any comments on this?
Yeah, it's not surprising that the traditional vendors would make that argument. This is disruptive and threatening to their business models. But you don't have to have SDN globally, and there's not just one SDN domain. There are many, many SDN domains. And so, for example, what I was showing here at the edge, that's an SDN domain. You can scale that just fine. If you go into, say, Google's data center, that's another SDN domain. And that's how they run their data centers. If you connect their data centers together through their WAN, that's another SDN domain. Each one of those have been demonstrated that you can scale those just fine. Now, there is a limit to how the time bounds that you have to react to certain events. And so you sometimes will, in the switches, you instruct it what to do, but that doesn't mean that there isn't some local activity that happens there as well. So you might load balance between ports or make failover decisions between ports as a local decision. So there's still sharing of responsibility, but you now have the opportunity to centralize it. And I think that's the important point. But in terms of feasibility, the SDN controllers have demonstrated that they can scale quite large.
Thank you, Larry. Second question, how does Aether implement the filter smarts to traffic steer packets to its edge as a platform versus central cloud? Are packet marking being used or DNI or to arrive at the correct location? This is from Brian Pepito.
Yeah, that's an interesting question. There's a lot of opportunity to be innovative there. First of all, actually, let me just bring this slide up because it's probably reasonably useful. You are programming these switches to do pattern matching. And if you know a particular field in a particular Ethernet header or IP header or so on, you can catch those packets and instruct it as to where to forward. So to a first approximation, we are primarily bringing the IP world into here so that you are talking, this drone has an IP address. And so I know this drone controller knows it wants to talk to that drone. It sends a packet to that IP address. Service discovery or address discovery becomes an interesting problem. Now, if you didn't know what packets you wanted to catch, then you might do deep packet inspection, but you could actually implement that inspection in the switches. So there are still opportunities to do DPI and then do intelligent things when you discover stuff you want to look at, excuse me, more closely.
Right, thanks, John. So next question from John. Thanks, Larry. What if any security challenges arise as the architecture moves to programmable wise lockdown configuration, mostly operator induced, or are the Kubernetes clusters a high payoff target? This is a question from John Quake.
Yeah, so I think it's a natural concern that I've just built an open source target here to attack. So there's several responses to that. First of all, just because it's open doesn't make it more vulnerable. In fact, there is a very strong argument that having all of this software open gives you some more assurance that you know what it's doing. If this were all closed inside of an eNode B that you bought from a vendor, perhaps a foreign vendor, then you might not know what was in there. But now you know everything that's going on in here, first of all. Second, this is being built using best practices in building scalable and secure clouds. So a lot of stuff that you used to be, you would spend a lot of time arguing, have I got that particular channel secured? You basically have taken the secure communication that was already part of building microservices and you're able to take advantage of it. So you don't have to resecure everything over and over. Your best practices apply. Third answer is you're now building the system that you can verify is behaving the way that you want it to behave. So again, without having shown you one of the demos, one of them attacked and compromised one of these switches. But because we knew what its behavior should have been, we were able to detect in another switch that this switch was the one that was misbehaving. And that's part of that verification and closed loop control. So this is, while it opens up a new attack vector, arguably it gives you new tools as well.
Mm-hmm. Thank you, Larry. The next question before I open up to the panelists is a runtime question. It says, as from Hangju, the data plane programs have to be, for current commodity programmable switches, the data plane programs have to be rewritten, recompiled, and reloaded to add a new functionality, resulting in interrupting the switch. Is it possible to do this more flexibly without restarting the switch?
Yeah, so that's a great question, and the way it's being used today, it is one is scarce. That those pipeline tables are a scarce resource, and there is a disruption. I forget the exact number. It's actually a fairly small reprogram time, so it's not catastrophically large. But being able to more flexibly control that scarce resource is a really interesting compiler problem. And so there's a lot of opportunity there. It is true that there is some disruption. So in one of the things you can think about though is I have a program that is fixed, but I'm able to change what it is I look for. So in the INT in-band network telemetry example, I don't change the monitoring program, I change what the monitoring program is looking at. And that's no different than a control operation to insert a new route. I insert a new zoom in on this. And the flexibility, that's then a runtime operation.
Larry, is there any paper on the stuff you talked about? Except for the SIGCOMM paper, right? Is that the one? That's the Pronto, right? Is there any other paper you have?
Yeah, so there are some. So just in NSDI, there was a paper from Nate Foster on Nate's the P4 guy. Nate has a paper on some interesting work that's happened there. I forget the title of it.
Okay, I open it up to the panelists now. We got about 5 more minutes. Anybody on the panelists before we go back to the audience? Tony?
Yes, I have a question for Larry, and thank you for your very interesting and informative talk, by the way. My question is, because we're the Institute for Assured Autonomy, throughout your talk, I was wondering what new challenges are created for assuring these kinds of networks, and especially as people decide to implement different forms of AI in managing these networks, because it's kind of wide open. So I imagine that there's a whole new class of challenges, and I'm hoping that you can comment on that.
Yeah. First of all, just as a meta statement, I think having the network as a programmable platform just opens up a whole new, this is in my view, a pretty big deal. And a lot of what has happened in the computing industry, and you've got Linux, you've got applications, and that whole ecosystem, that opportunity is now here for the, really for the first time. And so opening to innovation is, a big deal. There is a ton of opportunity to then mess that up, obviously. I'm not an ML AI person. I think that you've put your finger on a huge problem. Is what is the behavior you get out of an ML program? We've already talked about securing the actual infrastructure. That's clearly a huge deal. Every imaginable thing can go wrong, right? I think I kind of approach it.
That's why we're here.
Yeah, that's why you're there. I kind of approach it from the other side, which is there is now a tool that you have available that you did not have before. You have visibility and provable correctness out of your system. So there's a nice analog between, if you remember, sort of high-level specification, and it gets compiled down all the way into the hardware. The analog is what we do with hardware today, right? You trust hardware because it's gone through design steps where at each level you're able to make arguments about the correctness of what's below it. And we've just never had that opportunity in the network, and we do now. So if you kind of go back to that picture and you map it onto a hardware design problem, we're not there yet, but that's where the opportunity is.
Any other question from the panelist? Any other question from the panelist? Okay. I have a question regarding the potential collaboration from the universities with ONF. I know you started working on those. Is there something you can enlighten us?
Yeah, so this, just going back to this picture, you see some universities there. In fact, some of them are certainly our collaborators on Pronto, but others have come along and are now bringing up Aether. And so it is something that we're open to doing. We think it's actually a pretty nice platform for doing research on. So universities we can help universities. We got a bill of materials. You can build a small pod, you can build a slightly larger pod. We will, for the time being, manage it from here, but you also can replicate the management layer. Yeah, so we're looking to add sites to this, and we'd be happy to have other universities get involved.
Thank you. I had another audience question. How does the fine-grained network telemetry differ from S-Flow? I think maybe that's the last question.
It's not fixed. I mean, ultimately, it's not fixed. It's not what the vendor, it's not what the chip designer decided to give you. You can change it. So you can go, there's a lot of examples here, but you can go ask for this particular packet, which flow rule did you match to make your forwarding decision? No one thought to ask that question until now, and now you can program it to ask that question. So it's programmable.
Thank you. Last chance for the panelists. Anybody else? I think we reached the top of the hour. I guess I think we should wrap it up. There was another question on the security side, but I think you asked, is there any rogue node, fake node detection mechanism in Aether architecture? Further, are there any verification of the software deployed in the edge? What if some hostile changes are introduced and someone open up local base station on Flash software, right?
Yeah, I mean, that's the whole point of Pronto, is that you can verify that it did what you instructed it to do.
Okay. So with that, I think I would like to thank you for an excellent talk and answering, I think, almost all the questions from the audience and panelists. Look forward to hosting you in person whenever you're coming to DC area, Maryland or Baltimore. Please let us know. Anybody else, panelists, Cara, Tony, Ken?
Thank you, Larry. We appreciate it. Thanks for your time.
Thanks for having me.
Very interesting.
Thank you, Larry. This was great.
Thanks.
Thank you. Bye, everybody.
Bye-bye.
Thank you for attending. Yes.